Hey everyone. So, we all know about lithium ion batteries, right? They're in our phones, our laptops, our electric cars. But what if I told you there's a completely different type of battery that doesn't use any chemicals at all? Yeah, you heard that right. We're talking about mechanical batteries, systems that store energy using physical principles instead of chemical reactions. And honestly, they might just be the key to making our renewable energy grid actually work. Today, we're diving deep into the world of mechanical energy storage. We'll explore how these systems work, why they're so efficient, and how they're already being deployed to keep our lights on. Trust me, this is way cooler than it sounds. Let's get into it. All right, so what exactly is mechanical energy storage? At its core, it's pretty straightforward. You take electrical energy and convert it into physical work. That could be spinning something really fast, lifting something really heavy, or compressing air into a tiny space. Then, when you need that energy back, you just reverse the process. Think about it like this. Instead of storing energy in chemical bonds like a traditional battery, you're storing it in motion, height, or pressure. Pure physics, no chemistry required. This is all about spinning things fast. We're talking about flywheels here, massive disks that rotate at insane speeds. The energy stored in a flywheel depends on two things: how heavy it is and how fast it's spinning. There's actually a formula for this. The energy equals 1/2 times the moment of inertia times the angular velocity squared. Now, here's the catch. You can't just spin something infinitely fast. There's a physical limit based on the strength of the material. Spin it too fast, and centrifugal force will literally tear it apart. So, the real engineering challenge? Finding materials that are both light and incredibly strong. Let's zoom in on flywheels for a second, because these things are genuinely impressive. Flywheel energy storage systems are all about speed and responsiveness. We're talking millisecond response times here. What makes them special? Well, they excel at power quality and frequency regulation. You know how the grid has to maintain exactly 50 or 60 hertzes? Any deviation can cause blackouts. Flywheels can respond so quickly that they're perfect for smoothing out those micro fluctuations. And here's something wild: they barely wear out. Unlike chemical batteries that degrade with every charge cycle, flywheels can handle hundreds of thousands of cycles with negligible wear. Why? Because there's no chemical reaction happening. It's just physics. And physics doesn't get tired. Now, let me introduce you to the pinnacle of flywheel technology, the electromechanical battery. These things are absolute engineering marvels. Picture this: a high-strength composite rotor, often made of graphite or fiber composites, spinning at up to 60,000 revolutions per minute. That's 1,000 revolutions per second. And it's doing this in a near-perfect environment with almost zero friction. How do they pull this off? Two key innovations. First, magnetic bearings. Instead of physical contact, the rotor literally floats on magnetic fields. No touching means no friction, no wear, no maintenance. But it's not just about reducing friction. These bearings are actually part of the safety system. They have complex feedback control mechanisms that constantly adjust magnetic forces to keep the rotor stable during high-speed operation. One wrong move at 60,000 revolutions per minute and you'd have a catastrophic failure. Second, the whole rotor